Okay, this is the review for the second midterm. Just like the first, it will be on Monday, Wednesday, and Friday mornings during class time, starting up at nominally 7:55 and finishing at 8:30 or 8:31. It'll be on Canvas, and it will be in week 9. Again, if there are problems in submitting your materials, I think when Canvas closes at 8:31, it will remember the items you had within your boxes. But if there's a crisis, then just send me as quickly as possible your solutions. Okay, the material covered in the second exam is Bernoulli, which is fluid dynamics, excluding accelerating static fluids, which is 4.1. So weeks 4 and 5. Mass conservation in control volumes and conservation of momentum in week 7. The individual questions are in this order on Monday, Wednesday, and Friday. On Monday, we'll talk about Bernoulli and for free jets. On Wednesday's class, you need concepts of Bernoulli and conservation of linear momentum, which we covered in the first 2 sessions of week 7. And then again on Friday, Bernoulli again seems a staple to what we're doing, but also rotational accelerations. The appropriate expressions you'll need on the test are essentially restricted to the ones we'll talk about today, but you need to know how to be able to use them, of course. You know the ideal gas law to be able to define the equation of state of a gas. Remember that pressures are related to density, the gas constant for a particular gas, and the temperature. Both pressures and temperatures have to be in absolute pressures and temperatures. And alternatively, the other way to define it is in terms of universal gas constant divided through by the molecular mass of a particular gas. And so that's the ideal gas law. Bernoulli is a staple of what we've done so far. You know how it works. We define a control volume, which is enclosed by 2 streamlines. There's a velocity upstream and a velocity downstream. And we also know pressures and elevations of the upstream and downstream locations. And we can write Bernoulli in terms of pressure, elevation, and velocity heads in this way upstream. We can write them in terms of pressure, elevations, and velocity heads downstream. And hopefully out of this expression for 6 parameters, we know 5 of them, so we can solve for the remaining 1. In the event that we don't know what if we have only, for instance, 4 parameters, and we need to determine 2, then we can use conservation of mass to constrain the mass rate of flow in is equal to the mass rate of flow out. There's no accumulation in the volume, and therefore this is the term. Bernoulli is always for incompressible flows, so the densities will cancel out, and it's just the product of these 2 components. When we use Bernoulli, we define upstream and downstream conditions. A typical way to do this would be for a free jet, where you, for instance, define the conditions on the surface as 0.1, and you can define the conditions at some other location, such as the emanation point of a jet, either vertically downwards or horizontally outwards. The velocities would be identically the same. And if you solve Bernoulli for this expression, the velocity of the free jet is just given by the height of head above this. It doesn't matter if it's here, it would just be this particular head if that was the case. Or if it's further down, the magnitude increases because the length is growing. And of course, we did an example in class to be able to show that the acceleration of a packet of water here is just due to the acceleration due to gravity, which we can do by solving for the acceleration, the terms derived in terms of the material derivative. So that's Bernoulli equation. In terms of when we looked at conservation of mass, we talked about control volumes and moving and static control volumes. We always defined them in terms of what a static observer sees relative to a moving control surface or control volume, plus the velocity of something coming across that control volume, so that these are all vectors. In the x direction, it's just a single value, but the static velocity that you'd see of this water coming out of the gun would be the sum of the velocity of the ship boat multiplied by the velocity of it squirting out of the gun. So this is relative to the control surface, always this W value. And so that's worthwhile remembering. We talked about linear and rotational Newton's second laws. In rotational form, the centripetal force that results is equal to the mass that you're swinging around your head times the velocity squared in the arc. So this is meters per second divided by the length of the arc. If you make the arc smaller but still have the same velocity, then the centripetal force, not surprisingly, goes up. And we know what Newton's second law is in terms of linear behavior. It's just force equals, I guess there's a mass in here, right? Mass times acceleration. And this is just the streamline velocity, how it's changing with time. So this is just a rate of change of velocity. We talked about, it was in the week when we were already in the class, so I guess it was in week 5. We talked about the idea of fluid along pipes controlled by Bernoulli's equation. We could define the energy line and the hydraulic grade line. And it's useful to view things in this form because it shows us exactly that if we think of Bernoulli as the sum of 3 individual components, pressure head, elevation head, and velocity head, we can define these for different locations. So at this point here, clearly, atmospheric pressure, the big tank assumption is that velocity is 0, so all of the energy that's stored in this fluid has to be due to the elevation head. When it comes out here, it's no longer traveling at 0 velocity. It has to be traveling at exactly the same velocity at which it's coming out of the end of the pipe by continuity, by this expression up here. This defines the fact that the velocity, streamline velocity here, must be the same here and the same here. We may not know what it is, but if we find it, we can define it. And then at each of these locations, the Bernoulli expression is given by the elevation, the pressure up to this hydraulic grade line, and the velocity head. The velocity head is constant all the way along this pipe because continuity or conservation of mass requires that the velocity is the same. So the velocity head has to be the same and equal to this amount. But the components that make up the rest of Bernoulli would be an elevation, a pressure, and a velocity. And at this point, notably, the elevation would be above this point. So this pressure would be a negative pressure. So it would be less than atmospheric, since it's atmospheric at this point. And so the sum of Bernoulli terms would be a positive term, a negative term, and a positive term for each of these things. So that's a useful illustration, if you like, of what's going on in these systems. We talked about conservation of mass. We noted that conservation of mass is no different from drawing a control volume, which is the same as a stream tube. Mass rate in, mass rate out. In Bernoulli, there's no accumulation. But if we use Reynolds transport theorem, we can write a term which relates to accumulation. And this accumulation term are these two components. And they relate to a static volume and a change in density of the fluid that's injected, say pumping up a tire, or a constant volume and a change in constant density and a change in volume of the control volume, such as filling up a bucket, where the control volume size changes to be able to accommodate the inflow. And so the sign convention for these is important to note that increases in density or volume with time, such as this term and this term, are both positive in increasing. And the sign convention for the mass flow rates, which is given as the density, the cross-sectional area of flow, and the volume and the velocity relative to the control surface, are given by the sign convention, where this term really includes a dot product, and that dot product means that mass flow rates out are positive, so V2 would be positive, and mass flow rates in are negative because they're in the opposite directions of the unit normals. So this is always the sign convention you have to remember for conservation of mass. When we look at conservation of linear momentum, then what we do is we can write again Reynolds transport theorem. This is the expression that results in that the sum of forces has to equal the sum of mass flow rates multiplied by velocities. These mass flow rates exactly follow the convention here, where positive is out and negative is in. And so that's kind of shown here in these values here, is that flow rate into the system is negative, flow rate out of the system here is positive. It's across the control surface, so this is a flow in the z direction, but it doesn't matter because mass is just a scalar quantity, not a vector. So it just goes across the boundary. It doesn't matter that it's orthogonal. But these vectors, this is a force, these are forces, and these are velocities. So mass is a conserved scalar quantity, but the forces and velocities are vectoral quantities. And so one component of this three-component equation would just be that the forces in the x direction, sum of the forces, have to equal the sum of the velocities multiplied by the mass flow rates. And these velocities and forces have to be positive in the positive direction of the coordinate system. So for instance, a flow velocity in here, in terms of its Cartesian component, would be positive in the x direction across here. And a flow velocity across this surface would be positive in the z direction just because of these coordinate directions. So we have to be mindful of that. The other component is that we know that this term here, the mass flow rate, is equal to W rho A. And so W is always the velocity relative to the control surface. So if the control surface is moving, it has to be the velocity across that. But this velocity has to be the absolute velocity relative to a static spectator, because it's inertia that we're dealing with, and inertia is written in the frame of the reference frame of the planet, right? So this has to be relative to a spectator. And so we know from previous that from this idea that a static velocity, the velocity you see water coming out of this cannon at is equal to the velocity at which the boat is traveling plus the velocity it comes out of the nozzle and goes forward, so that this relationship is true. This is the static velocity here. And so when we define this velocity here, we can also define it as a relative to the boundary velocity and the velocity of the control surface. And that's important because we can look at static and steady control systems. It doesn't matter if they're moving. In fact, we'll have done an example with a vane where it's moving. And that is, if it's steady, then we can always write the equation. You can write it in this term always, but because the control surface is moving at a constant velocity, the mass flow rate times this constant velocity, since this must sum, as much must go in as comes out, this term here drops out. And so for a static and steady system, and actually also for moving and steady systems, then we can write this term here only in terms of the relative to the boundary velocity. And so this becomes W. But if we're dealing with an unsteady system, such as the case for the decapitated gas cylinder, then it's important that we include both of these components, because no longer is the system steady state. Steady means that as much goes in as comes out. And so it may be moving, but that's the requirement for a steady system. Clearly, with the decapitated cylinder, fluid is only coming out. So ultimately, it will be depleted. And so we're only assuming that it's steady state as a convenience, because clearly it can't keep on coming forever, because there's a finite volume of mass of fluid within the cylinder. And so we have to include both of these components to be able to accommodate that. And this is basically the essence of the problem in dealing with it, in that we realize that in the steady state, the velocity of this individual gas cylinder, if there are no forces restraining it, then it has to be equal to the velocity of the jet coming out of it, straightforward. And so we can rationalize that to be able to define the two conditions. One, when the forces applied to the system are zero, in which case these must cancel each other because the mass flow rate is not equal to zero. then the only way this term can be 0 is if these match each other. And the converse of that case, when the velocities, when the velocity of the control surface is 0, then if fluid is squirting out of the gas cylinder, then both m dot and w have to be finite, and then this force has to be finite also, just clamped in place. So the two conditions, either clamped in place where this force is equal to a maximum and this is not moving, or where this force is released and it will move at a maximum velocity. And so those are basically the expressions I think that you need to be able to complete the test. Okay, good luck.